All right, so as per your request, we're going to start with number 1, and then move on to 2 and 3 and 4. Numerical order, kind of cool. All right, so in number 1, they tell us the system consists of 51 electrons and 45 protons. Oh, this is like a chemistry review, right? Electrons, protons.
Right.
They want to know the total charge. Is the total charge positive or negative? Well, which one? Well, we got to do the Y first, and then what is the total charge on the system? So we can just use a generic Y for this one. Number 1. Yeah. Thank you, man. I like your sweatshirt. So let's see. Do different particles have different charges?
Yes.
Okay. Can anyone expand on that? Protons carry positive charge, and electrons carry negative charge. Which one has more charge, a proton or an electron? They have the same amount of charge. I mean, if it really screws you up, thinking positive and negative, rename them. Call them spongy and spiky, red and blue, whatever makes better sense to you. Male and female. All right? Anything that's opposite. So that you don't get messed up and go, oh, it's positive, it's bigger. No, it's just a different flavor of it. But they both have the exact same amount. So you'd probably write in here electrons carry negative charge, protons carry positive charge. Both have one quanta of charge. And then going back to your chemistry knowledge, what if I have one electron and one proton? What's the total or net charge? 0, or neutral. What if I have 10 electrons and 10 protons?
0.
0 or neutral. So what really matters to me is the difference in the amount of charge that I have. So if I have 51 electrons and 45 protons, let's start with the easy concept. Do I have more electrons or more protons? More electrons. How many more electrons?
26.
Okay. So 6 extra electrons. And for those of you playing along at home, that was 51 minus 45. Electrons and protons. All right. And I know that each one carries one quanta, which is 1.6 times 10 to the minus 19th coulombs. So the total charge, I'm going to call it big Q, is the number of charges times that 1.60 times 10 to the minus 19th coulombs. A lot of times I'll write 1.602 because that's the number that I have in my brain. And so my answer is going to be my 6 and my 1.60 times 10 to the minus 19th coulombs. And I'll pull out my handy-dandy calculator. Now remember, you could have your own version of these open on the computer and actually be getting them done at the same time and have less to do outside of class. I know it's an interesting concept, but for those of you that are looking to pass, it can be a helpful thing. And I get 9.6 times 10 to the minus 19th coulombs. And I bet that's right, but let's make sure I know how to enter it.
Oh.
I hope I'm right. So I'm going to put in 9.6. Then I'm going to use their controls to put in times 10 to the minus 19th. Incorrect. Where did I mess up? Oh. I forgot that would be negative, right? Because why is it negative, not positive? Because I have extra electrons. Yep. I'm waiting.
So there's more electrons.
Yep. All right, so on to number 2. What is the magnitude of electric force between these two charges if they're separated by this much? Okay. And all right, and then I'll let you do the second part. So number 2. So why is there even an electrical force between them? Good question. Are they opposites or are they the same?
They look the same to me.
Looks like they're both positive. So are they attracted? So that's a good start. Are they attracted or repulsed?
Oh.
They're repulsed. Okay, so they are repulsed. But why is there even a Why is there even a electrical force between them? Is it because they have mass?
Yeah.
What do you guys think? Is there an electrical force between these two particles because they contain mass?
Yes. No. No.
I'm just waiting to see if more people will participate.
No. No. No.
Why not? Because you seem very vehement in your nose.
Yeah. Because it doesn't say anything about mass.
Doesn't say anything about mass. I'm just assuming that they have mass.
So it doesn't say.
Is electrical force based on mass?
No.
What's it based on?
Cool.
Which is measure of charge. Right.
Yeah. There's something.
Kind of what I was trying to get at. There's an electrical force between them because they're both charged. I figure we have to go to the basics, right? What would happen to that electrical force if I added more charge? Yeah. So more charge, more force. What if I separated them?
Decrease.
More separation, less force. And then we could even do a little diagram. How does the force on one compare to the force on the other? Huh?
They're equal?
They're equal because forces come in
Pairs.
pairs.
Okay.
Hey. And then I would jump out to my good old handy-dandy equation sheet, which is right here, and I grab my equation for electrostatic force, which nicely says electrostatic force right above it. And let's see. Do I know the value for K? Yes, we do, because we have an equation sheet, and they even tell it to us in the problem, right? Coulomb's constant. I'm going to use my shortcut for it. 9 times 10 to the ninth. Newton meter squared per Coulomb squared. You're welcome to use the 8.899 or 889 that they give you. I didn't feel like writing all that because it's Friday afternoon. Charge 1. Which one do we want to use as charge 1? Point 21. It's in coulombs. Do I have to change that to microcoulombs or kilocoulombs or anything like that? Nope. It's base unit. And then I'm going to use the 0.15 coulombs, my second one. And then let's see, how much are they separated? 0.86 meters. Do I need to change that to centimeters or kilometers or anything? Meters is what we use. We should write that on the wall. Meters is what we use. And then pull out your fancy handy dandy calculator. Good catch there. And see what you get. I'm going to try mine.
Now, when you type K into the calculator, how would you type in that? Yeah,
Well, I generally don't put the units into my calculator because my calculator is pretty stupid, and so it can only handle the numbers part. But I look and say, oh, wait a minute, coulombs, double coulombs up top, that's going to get rid of that coulomb squared. Double meters on the bottom, that's going to get rid of that meter squared and just leave me with newtons. Because I'm smarter than my calculator. Sometimes. I got 3.83 times 10 to the times 10 to the 8th newtons. I wonder if that's right. No? You probably have different numbers than me. What did I say? 8? Yay! Alright, looking at number 3 here. What separation of electric force between these two charges have a magnitude of this? Ah. Yep. Yep. And in fact, I'm going to write on my Y, same as which one?
Number 2.
Number 2. Yep. And let's see, this time they just tell me different stuff, right? They tell me the force, 0.45 newtons.
Do you mind if I borrow this calculator?
I do, because I need that to do my work. Sorry. There is one on your computer, though. Equals, then K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. Q1. Which one should I use for Q1? The first one, because does it matter? Nope. And 5.9C. And I don't know the distance between them, right?
right?
No.
No, that's
No.
actually no.
That's the force.
No, don't.
We don't. So I do a little bit of funky algebra, right? And I'd end up with r squared would equal 9 times 10 to the 9th kind of swap the place of those two. What will be the most common mathematical mistake? People will forget to take the square root. So what I would suggest, write down like I did, r squared and then r. Because if you try to go directly to r, about half the people in the room will forget to take the square root. Trust me, because I do it myself. So, not a bad thing to do that intermediate step. So, I got 3.422 times 10 to the 11th meters squared. And now I'm going to square root that and get 5.85 times 10 to the 5th meters. And I'm going to hope that that's correct. Yay! All right, number 4.
Where's the second answer, Loda?
It's just the answer key.
You've been telling everybody that
Sure.
it's part of it. You didn't show up. Alright.
So we've got a spider mass of 0.15 grams. Do we want to leave that in grams?
Oh, no.
No, what do we want it in?
Okay.
Kilograms. Hangs vertically from one of its threads. Thread acts like a spring with this spring constant. What's the increase in thread length caused by the spider? This one is a diagram. And it's a diagram exactly like we had on those force diagrams we did. Mass, down would be force of gravity, up would be force due to the spring. That's your Y. And you might add in there some words like more force, more stretch of spring. And then the hows, just like we did that same thing. Sum of the forces equals 0. Which way do you guys want to call positive? Up. Okay, so we'd have force S plus a negative force G equals 0. So force of the spring equals the weight, right? I think this is like the third one in that packet if you missed any of it. And then I can look on my equation sheet. And I could grab things like, oh, the force of gravity, the weight is mg. The force of the spring is kx. So then I put those in. Kx equals mg. And what I'm looking for is x. Should I do the algebra now or put in the numbers? I'd rather do the algebra.
Alright, let's do the algebra.
Because all I have to do is I'm looking for x. So I divide both sides by k. Right? Pretty straightforward algebra, yes? Nacho, you get that algebra? Right, and then now it's just substituting in. My mass, I gotta make sure I put that in kilograms though. So let's see, kilo, 1,000. So I gotta move it 3 to the left. So I'm gonna have 0.00015 kilograms. What planet do I think this orb spider's on? I think they're on the Earth. That's the only one I know that has orb spiders. So I'm using the little g for Earth. And then they tell me K, which is 75.5 newtons per meter. Oh, and I can find X. And it'll be in meters. Let's see what I get. I get 1.95 times 10 to the minus fifth. Let's see if that's right. 1.95 times 10 to the negative fifth. Yay! 4 for 4.